Hello. Welcome. I am actually Benji, your new instructor. And today we're going to be checking this right corner of a problem. Search in a rotated sorted array. Now you may be wondering, Benji, why are you doing this? And well, I'll tell you, right? Yesterday I was looking at my screen time and it said 22 hours daily average. That was my computer. My phone says 4. Guys, that's 26 hours daily average. So I just thought, right, I mean, you can't, you can't do that. So here we are on LeetCode, solving this right corker. So let's check it. This is number 33. We're given an integer array called nums, and it's sorted in ascending order. And we're also given a target. So we've got to find this target in our array. So if nums is rotated at some point, at some pivot, so we've got some weird conveyor belt situation going on. What can we do to find this target? If we find the target, we want to return the index. And if we can't find the target, we just return a -1. So you might be thinking, well, Benjo, this is rather simple. You might be clueless. You might be like me and you might have no clue, which is all right as well. But something we could do to start is just look at every element, right? So we could literally just say for int I equals 0. And then I, as long as it's less than nums.length, because, you know, if nums is our diving board, and you've got to see how many steps you can go, the last thing you want to do is go past the end of the diving board, right? Because then you're, well, if you're me, you're drowning. So, you know, we want to avoid drowning. So we want to make sure we're within the length of the array. And we want to make sure we're less than the nums length, not equal, because the length, if it's 3 long, we actually only have index 0, 1, 2 that are within the array. 3, we're drowning. So then we can literally just say, for each element, if nums at I is equal to the target, then, I mean, we've only gone and done it, lads. Then we just want to return I, because that's our index. And then if we get outside this loop, we've looked at every single element in the array, and we don't find what we're looking for, well, we're buggered. So we just return -1. So if we just give this a quick run with our beautiful little test case, accepted. You best believe. You can see my other attempts here, don't worry about that, and you will see we are faster than 100% of Java online submissions. Now, that doesn't quite make sense, if I'm completely honest. But yeah, that really, I mean, it's quite encouraging, but it's got to be a better way, right? Because right now, in the worst case, we're looking at every single element. And we don't want to look at every single element. What we could do, though, is this log n thing. So we can have big O of log n. Log n is like, what is this meaning? But this is basically finding 2 to the power of what is equal to n. So if we've got n, and we've got log 2 of n, we're actually cutting down the sample size by 2 every single time, which is really good. So let's take a look at this example. Imagine this is what LeetCode had given us instead of its weird 4, 5, 6 blah malarkey. So we have an unrotated sorted array. Something we can do is called a binary search. Now this only works on sorted arrays, but we just happen to have exactly that. So how binary search works is we start at the left, and we basically create a pointer or a number. It's just an integer, and it's the index of the far left of the array. So this happens to be 0. And then we also do the same for the far right of the array. So this would be 6 in our case, but it's just the furthest rightmost index. Then what we do is we add 6 and 0, so we add left and right, and divide by 2 to get the average, or the middle of the array. So if we add 6 and 0, we get 6, and then divide that by 2, we get 3. So this becomes M. So this is our middle. What we do from here is, in a binary search, typically, we want to say, all right, is our target greater than middle? And if it is, well, we want to look at the right-hand side of middle up to right. And then if our target was, say, 2, we'd say, is 2 less than 4? Yes, so then look at the left-hand side of the array. So in this case, let's say our target is 6. We'd say, is 6 greater than 4? Yes, it is. So update left to be m plus 1. So L would come here, and then L would disappear. But before we do this, we have to check, is the middle element actually the target? Because if the target was 4, we'd want to do a quick check just saying, okay, is middle 4? If it is, return middle. Otherwise, it's got to be on one side or the other. So we do that check. Is it greater than 4 or less than 4? So that is a binary search. And what you do is you would just call this again. So you just do the binary search again. You'd find the middle of these two elements, 5 and 7. So you just add 6 and 4, which is 10, divide that by 2, and you get 5. So our middle would be 5, and then we check, is middle our target 6? It is. So then we would return middle, which is index 5. But I know what you're thinking, Ben, this ain't what we got going on. We got this sorted bollocks. So, are we just buggered? Do we give up? Probably. But we can't. So what do we do? Well, it's actually a pretty cool trick. So to keep log n time, right? So we want to divide our array in half every single time, right? Divide this by 2. So in this case, our left is this index 0, which happens to be a 4, and our index right is 6, happens to be a 2. Middle is right in the center. That is index 3, which is a 7. Now let's say our target is 0. What we do is we say, is 0 less than 7? Yes, it is. But also, this is the additional check, if it's less than 4, which is the leftmost piece of our array, then it means that it has to have rotated around. So if it's less than 7, but also less than L, so less than middle and less than L, we actually want to check the right-hand side because we know that our 0 has rotated itself to the other side. So that's basically the light bulb moment. That's all it is. But there's a problem. What if we have something like this? We're looking for a target of 1, and we've got our L here, we've got our right here, and our middle is 2. So this is where things get tricky. Is 1 less than 2? Yeah, it is. So let's check the leftmost index. 0, that's a 7. Is 1 less than 7? Yes, it is. So based on what we've just said, we check the right-hand side of the array. But then we really have bugged it because 0 is not, 1, sorry, is not there. We're never going to find it. So what do we do? And this is it. What we do is take advantage of the fact that our array is rotated. So it's technically still sorted if we do this conveyor belt thing. But somewhere along our conveyor belt, we have the biggest number touching the smallest number. Now, because this only happens once, right? There's only one biggest number and one smallest number. We know that if we have middle here, left here, and right here, this weird case where we have the biggest number right next to the smallest number only happens once, which means it has to happen either on the right-hand side of middle, including middle, or on the left-hand side of middle, but also including middle. Right? So if it's on the left like it is here, and our target is 1, we actually want to ignore this left-hand side, because this is just, it's just rubbish, right? 7, 0, 1, 2. That's not ascending order. That's not ordered at all. That could just be random. That's just a scramble. So what we want to do is look at our array and find which side of middle gives us valuable information. So let's say we know it's the right-hand side because the left-hand side buggered us last time. Say we know it's the right-hand side. So we know it's 2, 4, 5, 6 is ordered. We know that's good. Then we check our target. Is target less than 2? Yes, it is. So look at the left. And the reason we know this is true is because we know this is ordered. We know that this goes 2, 4, 5, and has to go upwards. We know it doesn't suddenly jump down to a smaller number, which means if it's less than 2, it has to be on the left. There's no way we could have a number smaller than 2 on the right-hand side, because we know that this right-hand side of the array is ordered. So hopefully that makes sense. It's kind of a bit confusing, but one of the sides of the array, at least, is going to give us a piece of valuable information. So in this case, it's the right-hand side because you notice 2, 4, 5, 6 is ordered. Whereas if we look at the left-hand side, including the pivot, 7, 0, 1, 2, that's not ordered at all. So that's going to give us some really weird, strange results. So our algorithm basically starts by asking which side of the array is organized, which side of the array should we use to get some information. And how do we do that? Well, it's actually not that bad. All we have to say is if the index, right, the number at index right is greater than the value at index middle, then let's use the right-hand side, because we know that this is in ascending order. Whereas if you look at the left-hand side, technically values on the left-hand side of middle should be smaller. So if we have some weird stuff going on, this value, the far left, is actually going to be bigger than middle. So that's how we know that this is just some random garbage and we don't want to look at it. It's going to give us bad, it's going to break the system like we saw in the last example, so this side, right? So that's what we want to do. So to clear this up, let's just do one final check. So if we have 0, 1, 2, 3, 4, or 1, 2, 4, 5, 6, 7, this is just like another unique case where actually both sides are valid. So you see 4, 5, 6, 7, that's a good order. Right, that's totally ordered. But also 0, 1, 2, 4, that's in order too. There's nothing that would break our system. So we can actually use either side to find target 1. If we're doing it on the left-hand side, what we'd say is 1 less than 4? Yes, it is. So go to the left. Notice nothing is broken. And then alternatively, if we look at the right-hand side, we just have to say, is 1 greater than 4 and greater than 7? No. Is it greater than 4 and less than 7? No. So it's not in this side, so that means we have to go to the left. So either side takes us to the correct side of the array, where we can update r to equal middle minus 1. So that might be kind of crazy and confusing. So let's jump into coding this boy to try and make some more sense of it. So we want to create an integer that is L. So this is the left-hand side of the array. And because it's the left-hand side, it's the start of the array. So we just want to set it to 0, right? It's just left. It's the 0th index. Next up, we want to create index right, which is going to be equal to nums dot length. But not quite. Because if we did nums.length and we had an array of size 3, we'd access index 0, 1, 2, and 3. But index 3 doesn't exist, right? That's drowning. So we're going to say it equals num.length minus 1. Now here's where we start the binary search. We don't create the middle yet because we want to make a new middle each time. So like in the first example, we have our left and right, we find the middle, and then we move one of the left of the right, and then make a new middle. So each time we want to make a new middle. And one of the questions you might be wondering is, when do we stop this binary search? Well, it's when left is greater than right. So our edges have crossed over each other. That's when we know we haven't found our target. So we want to say while left is less than or equal to right, because these are still all valid, we want to set int mid to be left plus right. And then make sure these are in brackets, because we've got to beware of some order of operations. We don't want to do right divided by 2 plus left. We want to take L plus R and divide that by 2 to find the middle. Right, so now once we've got the middle, we've got our questions. So we want to say if nums at mid is equal to the target, so remember this is just our check at the very beginning. If nums at mid equals to the target, then just return mid. So now we get into the serious stuff. Let's put our test cases down for a second. So what are we asking here? So now we want to say if nums at left nums at left, right, is less than nums at mid. Sorry, my bad. So this means the left-hand side is sorted properly, and the right-hand side is either some weird garbage, or it just so happens that both sides are valid, and either way, this is good. We know that the left-hand side is sorted. It doesn't really matter about the right-hand side if the left-hand side is sorted. So if this is the case, our nums at left is less than nums at mid. What we want to do is start asking questions. So we say if target is greater than, right, or equal to nums at left, and though target is less than nums at mid, then we want to update our r, because we want to look at the left-hand side of the array. So we're going to say r equals mid, but also remember, it's not mid, it's mid minus 1, because we've already done this little check. So we know mid isn't the target. So if we know mid isn't the target, we don't want to look at it again. So we can do mid minus 1 this time. And then if this isn't the case, we know that we have to check the right-hand side. So we're going to set L to equal mid, but this time plus 1, because we already know mid is not the target. All right, so now let's just check this out a little bit. So if our target is greater than the nums at left, sorry, and it's also less than the nums at mid, that means it's definitely on the left-hand side of the middle. So we want to update our r and move it over to mid minus 1, and then start looking at that next time. Otherwise, we got some violations. So either our target is greater than the mid, or it's less than the mid, but it's also less than nums at L. So either of those, which is just our else, we want to update left so that we start looking at the right-hand side of the array. So those are our little cheeky questions. Now, our else case, what is that? That's saying nums at L was actually greater than nums at mid, which means we have some random garbage on the left-hand side. So this is precisely this right here. So 7 is not less than 2. So we don't want to look at any information on the left-hand side. It's going to give us rubbish. So let's look at the right-hand side. And we don't need to do anything, any checks here, no else if. It's just otherwise, if one side isn't organized, the other side will be organized and ordered. And then we can basically ask the same questions. So we just want to say if target is greater than nums at mid, and target is less than or equal to nums at right. And the reason that we have to do this greater than or equal to here is because it might just be that our target is the rightmost value. So we don't want to say is it between. We want to say is it between the mid, because we've already checked the mid, and up to and including the target, because it might just be that we're looking for the target. If we're looking for 7, we don't want to say is it between 4 and 7, look to the right, because 7 isn't between 4 and 7, right? It is 7. So we want to make sure we're saying less than or equal to or greater than and equal to. So if this is the case, that we've got our target is greater than middle, but still less than or equal to the right, then we want to update our left to equal mid plus 1. Then in every other case, if something went wrong, we want to update our right, to equal mid minus 1. So hopefully this all makes sense so far. This is our while loop complete. So if we get to the end of our while loop, our binary search, right, mid eventually will be the target. But if we never find the target and we've gone through and left has crossed right, we've looked at every single element, we didn't find the target. So like LeetCode is asking, we just want to return -1. And that is it. If we run the same code with our test case, boom, accepted. And then if we run and submit this one, you'll notice that we get a wrong answer. Right, so if you saw it, you're probably screaming. But what if we had a two element array? We want to make sure that nums at the left is less than or equal to nums at mid, because it might just happen if we have two elements and we have index 0 and index 1. 1 plus 0 is 1, divided by 2 is 0.5. So as an integer, that is just 0. So our middle becomes the same index as left. So we have to make sure that we're saying if nums at left is less than or equal to nums at mid, then we want to look at the left hand side to give us some valuable information. So if we submit this time, sorry about that, we get a solution that is faster than 100% of Java online submissions. And so that is how to solve, or one way to solve at least, rotated sorted array LeetCode problem number 33. Hopefully that helped. Make sure to leave any comments. If you have other similar questions you need some guidance on, or if anything was confusing in this video, I would love to try and answer them, at least. Anyway, cheers.